When it comes to using data, many are relying on gut instinct, but that kind of decision-making is flawed. What they really need is certainty. It's the feeling when everything clicks. That's why Click is disrupting the industry with our active intelligence platform to help you transform data into informed action in the business moment.
Welcome back, everyone. This is part 2 of a discussion on what CDOs should know about quantum computing. And in this discussion, we have Dr. James Meng, Senior Scientist at the Supercomputer Center at the University of California in San Diego, Dr. Michael Haydock, IBM Fellow, VP and Chief Scientist, Data and Technology Transformation at IBM Consulting, Dr. Naguib Atia, former Distinguished Engineer and VP of IBM Global University, and Dr. Robert Suter, VP of Corporate Development at Quanta and former IBM Tech Executive. Welcome back, gentlemen, and over to you, James.
Thank you. Good morning. Let me share my screen. I'm going to take you through a very quick tour of intuitive learning of the quantum machine learning. And this is a part of the curriculum I established in UCSD extension. And this presentation will basically deliver 3 points that start from the classical machine learning algorithm building blocks. We are familiar with all the k-means and clustering and neural network and so on.
Excuse me, James, can you turn off your captions, please?
Turn off?
Yes, thank you.
Oh, okay, sorry, again. Okay. And the second part is compare the classical machine learning with quantum machine learning in terms of how it manipulates the data. This really is dealing with several major algorithms, Grover's and Fourier transform, and matrix inversion. It is important for me to say again that the quantum computer will not replace the classical digital computer, but it would augment it. And then we'll summarize what the future will look to me on the quantum computing. The first of all, it's the overview of the machine learning. Machine learning, even though it's a very large topic and has a lot of elements in there, but it really is, only has 4 major steps. First is to discover the data through classification or regression, and then simplify it, make it the clustering, and also reduce the dimension in order to capture the core essence, and then go into the semi-supervised learning. Again, more classification and the clustering, eventually go into the reinforcement and learning that eventually when you can get the conclusion out is really supervised learning. And the quantum computing machine learning is supporting some of the major elements, but the underlying process and the purpose are still the discover, simplify, decide, and activate. And the top view, I think I mentioned, and basically are in this 4 major block, and you see a lot of neural network that quantum computing is going to help us. Just to give you an example, what is clustering. So the artificial intelligence, for example, this is a case that you wanted to classify the information that you can somehow present them into a two-dimensional coordinates. And basically, they are the vectors measured by the calculation of distance. And then you can cluster them based upon the word use and also the embedding background among the data. Now you have 4 clusters, and then you can get the information out. For example, in this case is a detection of outside intruders and trying to hack into your system. So this particular user B belongs to a cluster, and that tries to get into server 3, 4, and 5, but all other cluster users are usually access only the servers within the cluster. So this will flag that user, and this is part of the machine learning. The second example is principal component analysis. So this shows a face recognition based upon Professor Cook's, and he used several well-known figures, and then use digitize them, row by row, and you have one very large matrix. Each one has a 1 million pixel data, and there are 5 of them. So it's a 5 by 1 matrix, and so on. But then you go through the singular value decomposition or principal value components, you end up with this principal component. This is a part of the, after you discover, you simplify from 5 million by 1 matrix into maybe 20 by 20 matrices for each person. And then you can use this principal component data to reconstruct. And so, for example, this is the original picture, and then you have the component of the PCA, and then can you reconstruct their images, and then you can compare the similarity with the 5 original images. So this just shows the classical machine learning. And this is another one, machine learning, is that not only you can analyze the picture, but you also can give the natural language processing to describe the scenario. So at the very beginning, you get a basically incorrect information, and then progressively it trains and to find it's a girl in red dress, and then finally after this is a convolutional neural network, and it will give you the correct statement that it's a girl in pink dress and jumping in the air. So from the initial to the final, and that's another example of a machine learning using the natural language process. So what's the point of showing all this? The same exact processes, now some of them could be done in the quantum computer. Intuitively, the comparison between the classical machine learning and quantum computing is that you have on the left-hand side, you have 3 bits of information, it goes through, you still end up with 3 bits. But in the quantum computing, if you have a 3 qubit, you actually have 8 possible states. You actually have more information. And from that, you will take the same input as the classical one and go through the quantum machine learning, and then condense what you learn from the 8 states and back into the three classical data digit. So if you are a user of this algorithm and you see the same input, you don't deal with any of that, but you get the output much faster and more precise. And the main approaches for quantum machine learning I basically think that there are four. Why this turned out to be the case is really largely based upon the quantum computing is all based upon very large dimensional vectors with complex coefficients. But the arithmetics is a very, very straightforward. And like the machine learning examples that I have shown you before, the very large number of the operation is simply calculating the dot product or the vector dot product, or it's the distance between the 2 points on that space. Some people can call that Hilbert space, but in here we just say the distance between 2 points. And the important thing is the quantum computing dealing with a very high dimensional. Remember in those face recognition, you got 5 million. 1 million, with 5 separate inputs, so 5 million vectors that quantum computing can deal with very quickly. Remember, 2 to the 20th power is a million. So basically, that 1 million data point will be handled by only 20 qubits. And that's where the power of quantum computing coming from. And the other one is the Grover's algorithm. This is for unstructured search. All these classical approaches is delivering the same end results, but Grover's algorithm can do it polynomially faster. That means if this takes n squared steps, and this will take square root of n steps. And then another very major contribution from quantum computing to the machine learning is because quantum computing is based on the vector structure, automatically it has the eigenvalue and the eigenvectors. The example I use on the principal value decomposition, that basically is the eigenvectors for that large matrix. So NLP word vectors, they all are leveraging the vector structure, but this matrix inversion is a lot faster than the Gaussian elimination in the classical one. And also the neural network, and fundamentally because the way quantum qubits are interrelated, connected, that naturally is fit into the neural network architecture, and therefore it delivers the results extremely fast. So I'm going to just give you a very quick view of what this is. This only shows that in a classical, and you are for matrix inversion n squared, but now it's a log n squared. From eigenvalues n squared is a log n to square. So basically, whatever n is, squared becomes a very large number. Take n is a million, that's 10 to the 12th. But the log n is only 12. 12 squared is only 144. And this is where you can see why the quantum computing is so much faster. Let me just quickly show you one example. This is a so-called the Grover's algorithm. It's for the unstructured search. This came from Jerry Chow from IBM. So, for example, we have 4 cars, and we're looking for this combination. And the way it works is that out of the 4 cars, you can have those 4 different combinations, and then the quantum computing will use a so-called unknown function, they call it oracle, and then through the cubic rotations, you're going to find out the answer is 0010 is this particular one. So now, why is this such a big deal? If you do the classical process, it will take at least 2.25 looks. But if you use the Grover, you will be only one. You say you're a big deal. But it is a big deal because there's only, 4 cubics. But when you go into the a million cubic, and that becomes a very huge difference between the two. And once the quantum computing goes through this, and this is how the circuit looks like, and then it will give you the answer is it's a 0010, the configuration that you're looking for, with a probability of 0.89. The others are much lower. So in terms of mathematical configuration, it looks something like this, but it basically take the, say, for 2 cubic, and we have initialization, and we'll do the phase change and then an amplitude. And I'm not going to go through the math, but I just give you some feeling of what behind the black box, or what does it do. And it's able to first pick up this particular answer and then flip it. And the quantum bit, it does is largely change the phase. And if you flip it, it's 180 degrees of flipping. Then once you flip, and then it has to re-normalize. It used to be everybody's half. Now the normalize, because it's a minus 1/2, becomes from 1/2 to a quarter. And then once you flip, and then you do another oracle that you flip again on top of the normalized value, and from a 1/2, it becomes 1. So that's 100% probability that you're going to get that. So in one operation, Grover's will give you the answer that it is that particular cubic. Another thing is the quantum Fourier transform. Dr. Haydock is going to use this, so maybe I just spend a little bit of time. So you start out with a cubic, 4 cubic, started with 0 and a 3. And say, for example, is you have this state. And so you have a 1, 0, 1, 0. So it's a 1, 0, 1, 0. This is the lowest binary digit. And then from that, you can go through the Fourier transform. All it does is change the phase. It changes the phase. So in the Fourier space, it looks something like this, but it basically rotates this first along that axis, and then rotate around the z-axis. And so each of this has been rotated. The Fourier, the frequency information. And from that, you can get, but the idea is not a math. Idea is that all of this is done in once, extremely fast. And then once you get the Fourier transform, you took the information from the unknown, the information you wanted to get it from, and the Fourier transform will give you the phase information. Then you can use the inverse Fourier transform to get their phase information, and that's what you want. And then finally is the inversion. So you have an input, and you wanted to get the eigen value out of it. And then you will go through the superposition, quantum Fourier phase estimation, get their eigenvalue, and then rotate to get their eigenvectors. So the math, this looks very complex, but the math itself is extremely simple. Arithmetics. Okay, now I'm summarizing. I leave a little bit more time for Dr. Haydock. So why the efficient future machine learning capability will be based upon QML? First of all, it's a capacity for data growth. Remember that 2 to the 20th power is a million. And when one day we have a 300 cubic, and that will represent 10 to the 90, that will be the entire information content of the universe. And that it's unimaginably large data capacity. So we will never run out of ability to deal with large data. So that's the number one reason. And number two is the QML enable assured privacy. I didn't show you the quantum teleportation, but this is based upon the quantum phenomena that you cannot copy quantum data. If you look at it, you destroy it. And as a result, the quantum machine learning is absolutely secure. There is no way that you can violate. The hackers will be out of business for quantum computing. The only place they can get in is through the interface with classical computers. And the quantum machine learning provides exponential speed up. Exponential speed up means that you use to deal with n to the power of power. But now you will be dealing with, square root or the logarithmic of them. I'm sorry. Okay. And so quantum Fourier transform extracts the eigenvalues very efficiently. So the vision for quantum machine learning is that you will have a quantum computer on cloud. You will link with terminal devices. In Asia, this is a very, very big deal. For example, Fujitsu in Japan, they already have quantum photonic devices that can interface between the quantum output and the machine learning. So this is all I have, and I will come back again after Dr. Haydock finished his. So we will entertain your question together. So I need to stop sharing, right?
Yep, I think it's good.
Okay.
I think I can take over from there. Hi, everybody. Mike Haydock here. How are you? I'm a IBM fellow with IBM Consulting. And what I wanted to do, I'm going to share my screen here for a moment. And I want to be able to share with you some work that I've been doing in the quantum area, primarily in the marketing sciences. But I thought first, maybe I'll tell you a little story about how we got to this particular place, okay? Dealing with marketing sciences. So I've been working a lot with machine learning forecasting algorithms and being able to use lots of external data to characterize these forecasts. And these forecasts are used in supply chains, retail, especially during the pandemic when all forecasting systems were pretty much defunct. So I got curious one time. I've been using Fourier transforms on some of this external data, like weather data as an example, and trying to take it from the time perspective and put it into the frequency domain, kind of similar to what James was just talking about. And I found that using these Fourier transforms really improved the performance of the accuracy of these machine learning algorithms when I ingested them as like an external data. And then I got curious one day and I thought about, I wonder if using a quantum computer, if I would get a different result. So in IBM, we have a facility called Qiskit. And Qiskit's a programming environment. There's lots of examples out there. The Fourier transform is one of those examples. You can jump on a quantum computer for free in the cloud, and you can kind of tinker a little bit. So I was sort of tinkering with this. And my real question was, is there a difference, okay? And is a quantum computer actually useful? Is there something I can do on it today on what I'll call relatively small quantum computers? And it turned out that it made a pretty big difference. And every time we did this experiment using the quantum simulators and the quantum computers, we've got kind of a better result. And so the forecasting accuracy improved. It didn't improve dramatically, okay, but it improved. And, every little bit sort of counts. And so the next part of the story is really about how I got involved in using a quantum computer in the marketing sciences environment. Okay, so I was asked by a team of IBMers working with the Adobe Experience environment. And so Adobe Experience is something where a user could be on a click stream, let's say clicking through Amazon or something, or a bank site as an example. And we want to be able to tee up what might be the next best action. So can we analyze what the click stream is in real time, okay? And then be able to turn around some kind of I'll call it a promotion or an intervention to be able to, really understand where this customer's at and to get them to do something that, this company would like it to do. So we'll call it a promotion because that conjures up kind of an image. So I was asked, is there any way of using a quantum computer in this environment? And so I kind of thought about it a bit. And the application I'm going to walk you through was the result of that inquiry. And so the way that I thought about it was really that the state of a consumer is really kind of a mixture of behavior, okay? And is that something that we could leverage a quantum computer on? So we weren't using a quantum computer really as a solver, okay? We were using it as a data transformation device. And so can I understand something that's really hard to kind of figure out? It's almost invisible, okay? The state of a consumer is relatively unknown. And so we might be using something like, a hidden Markov chain of that. So I thought a Markov chain might be kind of useful. So we decided to use this Markov chain. And then James in his presentation mentioned using phase transitions in quantum computing. And so what we were looking for actually is the phase transition, which told us that a consumer was, so it kind of rotated, as he showed in in his diagrams with the block sphere. And so that to me was really understanding kind of the dynamics of the system, and then being able to predict where was this customer going to go. And then the question is, could a quantum computer make that prediction maybe a little bit more accurate? Okay, and so that's how we got to the marketing sciences aspect of this. And so a couple of slides just as background, okay? I think James painted a really nice background in his presentation. And, to me, there's two real principles when I'm thinking about data transformation that might be useful in a quantum environment. One is superposition, which we actually leverage. The other is entanglement, which we have, let's say, a feel for, okay? We didn't explicitly use it in this particular set of experiments, but the superposition, to me, was incredibly valuable. And that's what makes quantum really different. And so to maybe articulate a little bit about this superposition, I kind of envision it like the portrait of Dora Maar by Picasso. And this is a really interesting picture. It was actually stolen a few years back and returned. And so, but I like this picture because it shows a lady, Dora Maar, and looking at it from several different angles. And I think that's the best way that I can think of, if I were going to explain it colloquially, to be able to say, what is quantum computing? And it's looking at things from different angles. And then it's really taking those angles and figuring out the probability of where we think that, let's say this picture of Dora Maar, if I had to choose one angle, what would that one angle be? What's the probability that that one angle is the right angle to look at? So I won't go through the mathematics underneath it, but in the middle of the page, what I'm trying to do is identify If I were using classical computing, I would put this in a vector, okay? And so this vector would be a series of rows and columns, right? And so in my graphic on the right-hand side, I sort of have this vector saying, well, I'm a little bit of red and I'm a little bit of blue, okay? And I want to know at the end, what is it that I am, okay? And then on the very last, let's say in the bottom of the screen, I won't walk you through the computation, but you square these values, okay? And then it gives you the probability that something's going to be red or blue. And so that's kind of, let's say, fundamentally how this kind of works. The next piece is really the Fourier transform. And a Fourier transform is not familiar to most business people. So when I started to talk to my colleagues about it, and especially my customers, I got a lot of the what's that, right? But it's an engineering concept that is incredibly powerful. And so what we were doing was taking forecast. And so if you look on the left-hand side of the screen, let's say in the time domain, and what we wanted to do was we wanted to change that point of view, okay, to a frequency domain so that we could decompose these various time series, let's say, okay, into their frequencies. I can project those frequencies forward, similar to what you see on the right-hand side of the screen. I could combine those frequencies together, and it would give me a forward-looking forecast that was incredibly accurate. So it's almost like I'm decomposing the time series, projecting the individual units, then recomposing the time series again. And so we use that principle to be able to work with this customer data that we have. And so why pick this Fourier transform? So when I started to study a little bit about quantum computing and having used the Fourier, the two graphics on the left and the right-hand side look almost identical. And so it seemed to me that a quantum computer was sort of naturally made for this particular kind of analysis. And it turns out that it's really handy. And the thing that we really want to leverage, by the way, is on the right-hand side at the very center of the circle, okay, you sort of see like an angle, okay? And that phase angle, when that phase angle is changing, we believe that the customer is changing their behavior. And I'll kind of show you how we draw that conclusion. So first of all, I always like to kind of start with the data. So the data we used for this particular experiment was web data, okay, where we took literally millions of sessions of a couple 100,000 consumers from a bank. And so you can kind of picture, let's say in a rows and columns, a row would be a session by an individual. That individual may have 100 sessions. There was no magic number. It was how many ever sessions we observed. But these were individual bank customers every time they got on the system. A column would be the web page that we labeled, okay, using numerical values. And that web page would be what page did they land on. And at the end of that stream, okay, if you can imagine that set of rows and columns, we would assign some kind of an objective. So what was the objective that the customer was trying to get to? Were they trying to seek out a loan? Were they trying to check their balance? Were they trying to write a check, et cetera? So this was banking data. But in the aggregate, I think we can represent this kind of data from all different kinds of data. Okay, so it was similar in concept to the time series data that I was using, only it wasn't a time series. So I called this an event series. But we can take any data, that data is time stamped, we can put it in a series of events, and we can do this Fourier analysis on that time series. So the idea was we found that there were 14 major motivations in this clickstream data that we could really tease out of it. There were 1,700 different pages that you could land on. So these were several different kinds of system depending on who the banking customer was and what system they actually utilized. This was a bank that had done a bunch of mergers. So they had lots of websites that the customer could get onto. So we kind of filtered through all of that, and we identified these 14 major motivations by a consumer. And then you can think about that as being states. So I'm in one state and I'm moving to another state. And the idea behind, let's say the use of Adobe again, was that if I could gauge which state I'm in, and understand which state I'm going to, I could put an intervention in that. Let's call that next best action, for lack of a better word. But I could take that action and I can try to bait the consumer to do something or motivate them to behave in a certain kind of way. Or if that consumer was seeking help, I might be able to pop a website up and say something like, would you like to chat with a banker or something like that? Okay, so the way that you read this matrix that's on the bottom right-hand side is I would identify what the state row is, and then I would come over, and the largest number in that row is a probability. Okay, and I've kind of circled that they're moving from state 7 to state 6. And so that's how you would read this. So every consumer had a unique Markov transition matrix. Every consumer shared the 14 motivations. So it was, they were someplace and they're trying to get to someplace else. And it was our prediction about where they're going next. Okay, so that was how we actually used it. And to apply the Fourier transform, what we did was we developed a signal. So across for a row, each row one at a time, we developed a signature. So what did that signature look like? And in the middle of this particular page, what you see is two different states of the consumer. So one state is the consumer is seeking a loan. And if you can see the colors, that would be in the blue. It might be a darker color, depending on the screen. The second state, which is in a lighter color, okay, it's kind of a beige, let's say, that state was seeking customer service. So that person was really looking for help. And you can kind of see that the two states are different, so that we could take a signature unique to that particular consumer, okay, so it's the click stream that they exhibited to get them to this particular motivation. And each consumer was slightly different. So it was highly personalized. But we can analyze these through Fourier transforms on a quantum computer. And what we did is we measured the distance between what we thought was going to happen, okay, and then what actually happened. So when we looked at where the consumer actually went and we took our projection, we could take the difference of that. And on this slide, you can see that those differences, in some cases, were quite different. So on the left-hand side, what you're looking at is a graph that says how accurate was I? And in the blue line, which is the top line, that line is about 20% different than the line underneath it, which was when we did this analysis on a classical computer. Okay, so what that meant was, using the quantum computer, it helped us identify the state of the consumer. And the output of the quantum computer was actually the building of this particular matrix. So for each consumer, here I'm illustrating two consumers, I'll call them 1410 and consumer number 3223. They each had a different matrix that got generated by this quantum. And then, so what we did is we took each row of this, let's say matrix, okay, of this series, and we processed it using the quantum computer. And so it went row by row. Okay, so this is something that we would have processed in the background because this was not a very interactive, let's say, environment that we were working in. And so even though it processed it fast, we had millions of rows. We ended up needing an 8-qubit computer. The maximum number of rows was about 158 rows, I believe, and it's someplace between, if you took 2 to the 7th and 2 to the 8th, it was someplace in between that. So you would take the maximum one, which kind of told us that we could actually use small quantum computers, do some significant piece of work on it, get advantage by it, okay? We really weren't looking for speed per se, okay? We were really looking for the data transformation and did it make a difference? It really made a difference. And so one of the clues that we got was being able to understand where we thought, based on the quantum computation, the consumer was spending their time. And here I have our customer 1410 is spending time in looking for a loan. The customer 3223 was spending some time searching for funds. And so what we would want to do from a next best action standpoint is take the values, okay, of that consumer doing something, right? So this is the lifetime value increase of putting in front of that consumer, if you're looking for a loan, and they closed that loan. Here's what it was worth to the bank. Okay, and if you're looking for something to put into your portfolio, here's what that's worth to the bank. So what we're trying to do is we're trying to maximize the lifetime value of these particular consumers. To be able to do that, we used in a classical environment reinforcement learning. And so we took our Markov matrix, we fed it to this machine learning algorithm, which to me, the best way to explain reinforcement learning is you're training your dog. Okay, so it's a heat-seeking missile around a reward system. So we train the system, what's the best reward we could have? And so this would be based on what we thought was going to happen, what actually took place, and then what leveraging the highest expected lifetime value of that series. And so we could make the right offer. We would send that offer to Adobe. Adobe is a content manager. It tees up the right content. And as that consumer is clicking, that consumer would be presented with the right material. And so what we did was, we used the quantum computer as I think it's probably going to be designed to be used, at least for the next 10 years, is it would be, think of it as a fast math coprocessor. Okay, so, off a classical machine. So a lot of the work that IBM is doing right now is merging these two systems together so we understand what should be processed on a regular computer, okay, a classical computer, what should be processed in the quantum environment, and then how does that happen, super fast. With that, I'll stop. Maybe we'll turn it back to Jim, and we'll have some questions and answers if we have it. Thank you.
Hey, thank you, Michael. JP, are there any questions for us from Huva?
There is one question that goes into a different domain than banking. I'll table this one for a minute because I have a question, a follow-up on the banking experience. This is a very interesting use case to me. If we add qubits and we go from the 8-qubit computer to, I don't know, 10 and 15 and 20, and by adding qubit, what are we getting? What value are we getting in this use case? Are we getting the ability to process more in real time, more customers, more accuracy? Like, can you give us a sense of what do we get with more qubits in that particular use case that you just described?
That's a great question. So this would be my my opinion. Okay, so we really weren't seeking speed per se.
Yeah.
Okay, so to me, it wouldn't be a matter of increasing the number of qubits, but it would be a matter of increasing the number of quantum computers that were available. So I could take this big array with millions of rows, I can decompose it in a parallel processing environment and shoot that out. And I know that's something, for instance, that that is at least on our horizon in IBM research, the folks that are really building the quantum computers. So not only are they building computers that are doing heavier processing with the number of qubits, so as a solvers, but also putting these things in parallel. And I think that would help it speed up a lot. So we ended up having to process this particular, we only used one computer, so one quantum computer. And it took a long time because there were millions of rows. So we had to submit millions of jobs. It's like one job per row, okay? And the governing factor was the number of columns that we have, which was the number of, the maximum number of clicks in a session. Okay, so for instance, you're on Amazon, you're bouncing around, and you took 20 clicks. Okay, we recorded, each page that you landed on, so there would be 20 entries into this row. If you did 100 clicks, you were, heavily shopping Amazon. We'd have 100, entries into that particular row, right? And we did that for every consumer, and we had about 100,000 or more consumers.
Wow, very interesting. Okay, there is a question from the audience. What can you tell us about quantum computing applications in digital health?
Boy, I'll try to take that one, and then because maybe I'll bait James a little bit. So to me, James showed some pictures up front where he was trying to decompose the pictures. So to me, that's, you're pixelating something. all right? And you're trying to decompose it into a series of matrix, and then through a series of the principal components, okay, or convolutional networks. You're trying to recompose that and figure out, what it is. So to me, the whole area of medical imaging would benefit greatly from quantum computing. And I think what you'd get is a more accurate image. That would be my instinct.
Okay.
Right. I can also add that one of the issue that especially for seniors like me, when I take a medication, I like to understand all the side effect and possible interaction, maybe with the B6, the 12 vitamins I'm taking. And that kind of detailed understanding is largely anecdotal. And I think with the large amount of data that and the interaction the quantum computing offers will enable more thorough potential interactions among all the different medications that you take. Something very innocent, maybe aspirin, and something very innocent, maybe melatonin. And that potentially interferes with your high blood pressure medication. People don't know that. And some of the interaction will lead to frequent urination in the night. So you try to improve the sleep or reduce the blood pressure, but you end up going to the bathroom more frequently, and you end up increasing the blood pressure, and nobody understands why is that. It's because some of the interaction was not, side effect was not fully quantified. And those interactions actually highly personal dependent. And so I envision in the future, given your DNA and all that, the age and all that, and you'll be able to figure it out, when I take this along with many other medications, that will instantaneously tell you that this interaction is no good. And if you can visualize, given the input and with the interaction with 10 other medications, that will figure it out, the 100 probabilities of which one has the largest likelihood. And that's a very vector structured, statistics that give you the probability. That's very ideally suited, for quantum computing. And in fact, why do we get the vaccine so fast this time? Yeah. It was because of the quantum computing helping the pharmaceutical companies to decipher the DNAs, and because all vaccines are based upon understanding all the spiral, proteins, and having a way to cut off their reproduction or prevent the receptor, receptions. And that is all because of quantum computing. Nobody talks about it because the pharmaceutical company ain't going to tell you how they get it, because that's their business secret. They're not going to
very interesting
advertise that. So that, to me, the probability just infinite, and it really is going to improve human life quality. And Dr. Suter mentioned about the climate change.
Yeah.
If we can have, just a better weather forecast, and also knowing where the cloud is going to be, and maybe have a way to, extract the moisture so that the rain will fall on where there is a fire, and that kind of things. And to me, it's the probability and the possibility is just infinite.
Yeah, quantum, if I can, quantum chemistry is a huge area that's being explored. And in fact, most of you probably had a cup of coffee or a cup of tea this morning, okay? So if you take the caffeine molecule as an example, and you're trying to understand what the energy states, the probability of being in a certain state at a certain time, that almost takes the biggest quantum computer, just the caffeine molecule that we have today. And so it's pretty consuming. And so there's really a long way to go, in using it in a chemistry environment, but the potential is huge, as James is saying. And the drug companies are going to benefit, tremendously from this, and the consumers are going to be healthier. It's really just, I like the way that James said it. It's getting the regimen that you take on a daily basis right for your own body. Right. And I think that's a huge potential.
Very interesting. So for the audience, feel free to submit the questions. We have another question, which I'm going to read. Along with qubit power, optimization of algorithm would also be important for business problem solutions in quantum computing space. How that skill is shaping up?
I work with a lot of optimization. My background is in operations research, and so I've got a little bit of an opinion on that. And we've done a lot of work in optimization. We have a huge optimization group in IBM Research working in this area. So the most promise is something. Maybe this would, people with that background would know something about the traveling salesman problem. Okay, yes. and it's just an NP hard problem. Okay, and so that problem takes a really long time, probably intractable. Okay, because of the time that it takes. And by nature, it's a combinatorial problem. So the more routes I put out, think of if you're a FedEx or a UPS or something, how many routes you're doing. So there, just millions of routes. Okay. Yeah. And so this, this is, 2 to the millionth or something. Right. And so that, to be able to solve those kinds of problems, I think are going to save companies a ton of money. So the ability to use this as an optimization problem, especially when it's combinatorial, I think that those kind of problems now become tractable. So what we've done over the years in operations research is we've really kind of relaxed those kind of problems. So we'll do something like a simulated annealing or something that relaxes the objective and, subject to the constraints. And I think those things become real now. So that's the promise there is just huge.
Interesting.
Right. Actually, let me give you one example. And that was a 2017 Volkswagen, the car company, sponsored a traffic optimization from Beijing, China to Beijing International Airport with 100,000 taxi, just 100,000 taxis, not general public. And they were able to use the D-Wave. It's the Canadian quantum computing. They were able to optimize the route. It's like in 3 seconds. So all the taxi drivers are given the optimized configuration. So do not take the main trunk, but take a side road, bypass this, and they were able to resolve it in 3 seconds, which the classical computers couldn't handle it. They did another one, 2019, in Thailand, Bangkok. And then that was sponsored by Japanese motor companies. So now we extract and generalize this kind of optimization to the supply chain optimization, and we would be able to see where the problem was to prevent the supply chain, gigantic pile up we had a year ago. If we had that kind of ability to bring the data and structure it and help out. So instead of everybody going to Long Beach, maybe some of the ships should go to Seattle, right? Or some ship just goes through like Panama Canal, but that kind of things. It's just that when Dr. Suter made his presentation, it struck him in my mind is that there are 2 largest group of quantum computing application. One is optimization, and the other one is the detail. They call it simulation, but it really is the basic physics. Like dealing with the caffeine molecule, and that kind of things. But the optimization is exactly what the chief data officers are supposed to do. That's your value. If you're being a chief data officer, you cannot optimize your supply chain or whichever chain, and there is always a process chain that you have to deal with. And to optimize that is a very much a chief data officer's focus. So I hope one day that chief data officers should not become the quantum computer expert, but you should be aware of the potential. Much like that 10 years ago, we didn't think AI is going to be this big, but now if you don't deal with AI, you can hardly stay in the data business.
Yeah.
Thank you.
So I have a follow-up question on this. Maybe staying in banking, that's my background, banking. In your experience of what's going on at the moment with banks, do you see the CDOs in those banks being the driving force in bringing quantum computing, or at least thinking about quantum computing and bringing use cases and testing and stuff like this? Or do you see the driving force from other areas of the banks, whether it is the business itself, the CIO, the CFO, a research department, like an internal R&D department, or is it the CDO really?
Michael, you want to take first?
Yeah, I'll take the first crack at that. I think it's the CDO understanding the business. Okay, that's kind of where I see it. Because, for instance, in banking, if I went to the investment area, there's a huge environment around quantum computing, trying to understand how to improve investment decisions. Okay, yeah. So these would be either portfolio optimization or specific instruments, the behavior of specific instruments. So the CDO understanding that the business has these needs, okay, and then being able to say, hey, I think I can help you with these needs, right? Yeah. I think that to me is kind of where the confluence is. Right?
But do you see this, right? When the CDOs, when a bank calls IBM and says, hey, we want your help with quantum computing. We have some use cases, we want to test them out. Who is calling? The CDO today?
It could be either. It could be either. It depends on the relationship.
Okay.
But eventually, I think to get something actually done, you have to have all the parties locking.
That's right.
Locking in lockstep, right? So that's what it requires to get actually something done. So you don't want to leave anybody out, okay? But a lot of the CDOs are they're just excellent that we run into, really curious. They're all over the business, okay? So who makes the call is probably kind of a little bit indifferent, I think.
Got it. Okay.
Right. Yeah, I can add that. I know Goldman Sachs has a little research group pushing quantum computing. And I think the person who will call are most likely to be some of the junior interns, because they really carry the spark of enthusiasm and they see the light, they see the potential, and they are looking for supporting evidences from the larger companies, and like from Michael and all that, and to go back and help educate the CDOs. But CDOs in this conference, CDOs should maintain an open attitude to understand that that quantum computing is here to stay. It's not just a flash of the pan, and also the quantum computing do hold the potential. And I have read articles that on Wall Street that they actually use quantum computing to do the daily margin call reconciliation, because it's a huge amount of data that they have to, but it has a fixed formula. So, but that the process speed is the issue, because you wanted to deliver the ETF, instantaneous value, you don't want to wait for 2 days.
Yeah.
And so I remember reading those, so I know it's alive, but it may not be openly publicized.
Yeah, very interesting. All right, well, we have come to the end of this session, in this two-part session on quantum computing. So James, Michael, Naguib, I really want to thank you. This was very interesting. I feel I've learned a lot about it. So thank you very much for all these insights. We are going to break.
Thanks for having us.
Thank you.
Thank you. Pleasure.
We are going to break for 30 minutes in track 6. And then the next session will be at 11:30, and it will be with my co-producer, Andy Palmer. So please be sure to come back. Thank you very much.
Hey, JP.
Yes.
A real pleasure working with you.
Same here, same here. This is fascinating. You know, I like spending all my career in banks and business and hearing like the new frontier from you guys in academia but also with experience with business as well was really great.
Hey, but just a little bit of marketing. Your old bank was that the Bank of Paris?